stuff out before the recording. This is not going to be fun now. Zero fun can be had as we talk about ribbon microphones. Okay, so ribbon microphones is not in the notes. We're going off note here.
I'm ready for this.
So I was educated recently about a thing called ribbon microphones. And I thought they were kind of fascinating, so I thought I'd talk about them in class today. So there are many types of sensors that operate on some sort of principle like this, where you take some sort of mechanical motion, or you take some sort of pressure or force, or you take some sort of thermal energy, and you do a transduction of that energy to the electrical energy domain. Okay? And that's where usually your sensors are going to be effective for you, because before that point, you won't be able to do any sort of readout, amplification, etc. of your signal. So a microphone is an example of a sensor that's doing mechanical to electrical transduction. And the operating principles of the ribbon microphone are pretty cool. And they were actually the first high fidelity microphones that were produced, and they today are considered by a lot of audio engineers to be the best, or for certain applications the best microphone for getting good quality sound recording of voices and of certain musical instruments. So they're pretty cool, and they still make them. They even make like the replicas of the original ones, because it's become sort of like fetishized a little bit, the originals, but pretty cool. So I'll draw a little diagram of what these things, how they operate. So the first thing is that there's a piece of aluminum foil that is corrugated, and this corrugated aluminum foil is like 6 microns thick or something like that, like very thin aluminum foil. And the reason for using aluminum, and the reason for using such a thin aluminum, is to have low mass so that you can get nice motion from small vibrations in the air motion. It's corrugated to soften the tension a little bit. This is going to be a little bit like a vibrating string, right? If it's the more tense you make it, the tighter you pull it, you'll change the acoustic characteristics of it. It'll change the frequency that it'll want to vibrate at. And it'll also restrict motion. The tighter you pull it, the less amplitude you're going to get out of it. So having this thing move through the air, we'll see in a moment, is going to be how we're going to get a signal out of it. So it's got to move through the air. It can't be too tight. Yeah. So from the front view of it, so this is the side view, the front view of it looks like a little strip. And this is, I mean, what does to scale mean on a screen like this? But these are like a couple inches in length and like 1/4 of an inch wide. I mean, just really roughly. And the folds from the front, show up looking like this. And what we do here is take the ends of this foil, and it's so thin you can't really solder this stuff. So what you do is you compress it to a contact, like a copper contact, and with some good compression on there, there'll be good electrical contact. You can put some sort of flux on there to help. And getting that contact compressed allows there to be an electrical connection across it. That electrical signal will be generated by the movement, the motion of this foil in a background magnetic field. So the background magnetic field can be generated in a number of ways. It looks like the old school ones are made with like a couple U magnets like this to generate a pretty uniform magnetic field. The idea with your magnets is to get, doesn't actually matter which side's north, which side's south, but is to get a magnetic field that's running across the foil. And similar to our operating principle for the motor, but opposite, we have this transduction between electrical energy and mechanical energy when we have something moving in a magnetic field that can conduct electricity. So what we did to make a motor turn is we flowed current through a wire in a magnetic field that created a force, the Lorentz force that turned the rotor. Now, you can run those the other way too. You can have some sort of mechanical energy that's generating it via some like turbine or via a gas engine or something like that that's turning a motor on the mechanical side, and you can harvest electrical energy from it. That's a generator, of course. What we're doing here is more of the generator style, where the mechanical motion is going to transfer its energy through the acoustic wave, the air moving, into this ribbon, and the ribbon's motion in the magnetic field will induce a current through it. Okay? So this is the type of thing that, sensors usually will work, in some way like this. I mean, sometimes you don't need that magnetic field, sometimes you do. Sometimes you can use a capacitive effect or resistive effect that changes with some parameter in the world, and that's what you're sensing. But this sort of transduction is really important in a lot of cases. Motors, and generators, but then also sensors of all types, of many types. So this is our sort of mechanical side. The electrical side, we won't go too far down the electrical side modeling path, but we will include the inductor. So typically an inductor is placed here. So the inductor essentially decouples the low frequency or the DC component of the one side from the other side. So you could have different grounds, for instance, from one side to the other side. This will pass through, though, any of the higher frequency stuff, because that's going to be AC signals. Those sinusoids at higher frequency will come right through. Yeah.
Did you say inductor or?
Sorry, a transformer. Did I say inductor?
Yeah.
Sorry. Transformer. A double inductor.
I was kind of confused.
So yeah, thank you for clarifying. This is definitely an inductor. Okay. Transformer. Oh my God. Okay, I may have gotten 4 hours of sleep last night. So pardon my lucky. There might be more of those. Keep on me today. I'm probably going to do that a lot. So yeah, I ran out of caffeine. This is This is just water. I ran out of caffeine like an hour and a half ago, and it's starting to come into effect. So this is motor-like, and there's going to be a transformer constant associated with this transduction. We'll just call it Km, like a motor constant, but it's something that we would need to do either a pretty detailed analysis to figure out, or we would need to do some measurements to figure out what this motor constant is. So that electromechanical interaction, we'll say can be modeled with a motor constant, and we'll try to come up with a dynamic system model for this system. So we'll do first a linear graph model. So the linear graph is going to have a mechanical side, and the dynamics of this foil are actually pretty complex. It's got, it's a continuous body. It's flexible, right? So it's not a rigid body even. It's a flexible body. You could think of there being motion in the axis of interest, which is in and out of the board in this case. Motion of each point on this. And this thing, it looks a little bit like a membrane, right? That's like stretched in between two surfaces. There's a lot of analysis that's been done on membranes, like rectangular membranes or circular membranes, because they're very common, and there are analytic methods for solving the partial differential equations that describe them, okay? This particular case has this corrugation, right? The folded look to it. And that bent corrugation is likely something that has not, I don't know for sure, but probably there's not been a lot of analysis of that shape. Pretty complex to get into the details of how each point in the membrane is going to vibrate. Now, if you take the vibrations class, you'll do probably some like membranes, like rectangular membranes, but probably not shapes like this. This involves a pretty difficult and significant effort in analysis. But we're going to try to model this thing as a second order mechanical system, okay? We're going to lose some stuff in that. So we'll just do like a spring mass damper system here. It's going to have some mass as it vibrates. It's going to have some spring constant, springiness to it. It's going to have some damping because you're going to have this thing moving through air, right? And there will be some loss of energy in it to the air by moving air around. So the model is not going to be perfect, but I would not be surprised if we could get a pretty good model just using a first order model for the system. A more detailed analysis would allow us to discover what we would call like higher modes of the system. So this thing wants to vibrate at a given frequency, and it's natural or resonance frequency. That frequency probably has multiples of it at which this thing wants to vibrate as well. So there will be other modes, but they'll be smaller. So if you want to get into a really detailed analysis of this, you'd need to be able to do an analysis that took into account these higher modes. We'll just take a second order model, and that'll give us one mode, probably the dominant mode. We'll try to capture the dominant mode. Yeah.
So is this transformer is like amplifying the signal?
The transformer's not. Well, it could. I mean, that could be used. I don't know if they tend to have large ratios. It's not really amplifying in the sense that amplification we typically take to mean that it increases the power of the signal. We can trade off voltage and current with a transformer, but we can't add power with it. it will later need to be amplified. You'll need, for this, a very small current is going to be generated. So you're going to need to amplify that current with a nice low noise, flat frequency spectrum amplifier to get a real audio signal out of it. So later it'll be amplified. So you could put this into like an op amp, for instance. Past this, but we won't model it that far right now. But you could model that part too. So for this, it'll just be very, very small motions that'll be happening, very, very small voltages generated, but significant enough to consider. Okay, so let's do that. Let's also add in here on the electrical side. Let's put in a resistor here because this is going to have some resistance associated with it. Aluminum's not the best conductor. And we also have these contacts that are going to have some resistance associated with them. So we'll say there's some resistance here on this side. Yeah?
So since aluminum has no, isn't aluminum not magnetic whatsoever?
Well, it has current running through it. So the current running through it allows it to interact with that magnetic field. So it's not ferromagnetic. But when you run current through any material, it'll interact with the field. So good question. Good question. It's not an ideal conductor. I don't know if anybody's tried to make these things out of copper. The downside is the mass would be larger, and probably it would be less strong. So it would have to be thicker. If you did it with copper, though, you would have less electrical resistance, so that might help you with loss in signal. So I'm not sure if anybody's ever tried that, but yeah. Aluminum's the classic one that people have used. Actually, people now, I found one that they make now that uses carbon nanotubes for the ribbon, which is cool. You can make it 1 atom thick, so very thin. And then, they probably weave it. I actually don't know how they're constructing it, but they say they use carbon nanotubes to construct it. So they could put like 3 on there and call it, carbon nanotubes. I don't know what they're using, but they sell it for a cool $1,200 for a microphone. So no big deal. Hey, I wish. This is a condenser type, I believe. So not ribbon. Okay, so we've got this model. Let's draw our linear graph then. We said for the mechanical side, we do a mass spring damper model. So we'll have a mass node here. And then we'll also have a spring, because this thing is going to have a spring. We're gonna tension the foil, not too tight, but we're gonna put a little bit of tension on it. It'll definitely have some vibration motion, which is important. We want to see this thing have a sort of vibratory motion. It has to look like the pressure wave coming in, right? The pressure wave coming in has that fluctuation in signal. So we're definitely going to have a spring constant, K, and we're going to lose some energy here, at least due to the motion in air. Yeah.
What are we calling ground in the picture itself?
So the mechanical ground, you could just say like this side over here or something is fixed to a mechanical, like the chassis of the microphone. So this would be the mechanical ground, so like the chassis velocity, which we'll take to be 0. If it's significant enough to matter, you're using your microphone wrong. So, and then we've got the force source. So we've got a source that's going to be acting on this ribbon, right? So it's a pressure. So if you took that pressure and you looked at it, across a surface, you would get a force, right? So I think that the force source is the right source for us. This is going to be the acoustic forcing that the air pressure causes on the foil. And we'll just assume that we take the positive direction to be in the same direction as the force source. We didn't draw it in the diagram, so let's do that. And then we've got this transduction. So the transduction happens through something that's very much like a motor. So we'll say that is done by a motor constant Km. And since it's just like a motor, it'll actually have the same, we don't know the details of it other than it's going to look a lot like a motor. So we don't know what Km is, but we know it'll be a transformer like a motor is a transformer, meaning a system dynamics transformer, not an electrical transformer. So we have side 1 and side 2 of the transformer. And this ground is the ground here, right? So that's this ground. It could be different than this ground because we have them decoupled from each other's ground when we use this transformer. So there's the one electrical ground. We put a resistor in here in line with the electrical transformer. So you're going to have a resistance R, and then that's going to interact through the transformer, the electrical transformer, to the output side of the circuit. So this is also a transformer with transformer ratio N. We could make these grounds the same, or we could leave them separate. Probably is going to depend on application, and I don't know what they typically do. So we'll leave them separate for now. And we could connect up like the amplifier circuit and all that. We've got to stop the buck somewhere, so we'll just leave it open here. And we'll just look at the voltage that gets generated at this output as our output. So this is plus, minus, this is our V out. And so here you see the same thing, V out. It's just equal to, we didn't label it, so this is side 3, we'll call it, and then side 4. So V out equals V4. So now we'll do the rest of our dynamic modeling, which the first up is the normal tree. We'll use green and draw on top of the linear graph. So the first thing we select are A-type energy storage elements. Oh, cross-variable sources. We don't have any though, right? Sorry, I skipped it. We don't have any cross-variable sources. Thank God. Okay, all our nodes are also in there. Okay, hold me to what I tell you. So we have to connect all these nodes up to our tree. A-type energy storage element selected. And then we have the two transformers, okay? So the rule is that you have to select exactly one of each of these pairs, right? So 1 or 2 and 3 or 4, okay? We can't select one or it creates a loop, right? So we're stuck with this side. And on the other one, if you select 3, which seems fine, you don't reach this node here. And so you have to select this side in order to reach that node with your normal tree, which means now down to D-type, you have to select your resistor here. for your normal tree, and that's all of it, right? Any other elements added would create a loop, and we can't do that. Okay, so
Wait, can you move it down?
like this?
Yeah.
Great. So that's that. Okay, now I'll start numbering things. That was 1A, I guess. This is 1B. We've got primary variables, right? So our primary, we look for cross variables on branches. So we've got VM. All our cross variables are V. Some of them are voltages, some of them are velocities. It's clear from context which is which. VM, V2, VR, and V4. And then through variables on links, FS, FK, FB, F1, I3. Okay, so that means our secondary variables are just the opposite. So we have Fm, the force on the mass, F, what did I, oh, this was for V2. So it would be I2, good. IR, I4, and VS, and VK, and VB, and V1, and V3. Great. See, we've got the state variables. State variables are, we look for A-type branches, the mass, right? If the cross variable is a state variable, VM. We look for T-type links, so we see that K here is a T-type link, so its our through variable FK is state variable. So what's the order of our system? 2. So vectors, we'll do x equals, just the state variables, VM, Fk, input, we just have the forcing input, and the output, which I think we're going to be most interested here in the velocity, well, the position of the mass would be better. We kind of want to see how this thing moves, right? So let's look at the position of the mass, which we'll be able to get from the spring, right, using Hooke's law. And we'll also look at the voltage out. Okay. Okay, so elemental equations. We need to write down our passive elements here. So we've got M, K, B, R, and then the two transducers, 1, 2, and then 3, 4. Do you guys mind if I use prime for a derivative? Okay, let's do that. Vm prime equals 1 over m Fm. Fk prime equals k Vk. Fb equals b Vb. Vr equals IR times R. Okay, so 1, 2 is a sort of motor relationship. So we know that V2 equals Km, the motor constant, times the through variable, or sorry, the across variable, which is velocity 1. Now, through variables are related, so it's going to be I2 equals 1 or negative. Now, this was 1 over, wasn't it? It was 1 over Km. 1 over Km, and it's negative Km times F1. 3, 4 is the transformer, so it has V4 equals 1 over N V3, and I for the current is equal to negative N I3. Cool. Elemental equations. Done. Continuity. These equations are going to be for the branches, right? So we could do a contour right here for the M branch, which tells us that the force leaving this contour, Fm, is equal to all of the force going into the contour, which is Fs minus Fk minus Fm minus F1. So we have Fm equals Fs minus Fk minus Fb minus F1. Okay, so the next branch we can consider, we have to do one for each of these. So we could take, say, this contour first, which is going to say that I2, which is leaving the contour, has to equal everything going into the contour, which is negative I3. So I2 equals negative I3. So I2 equals negative I3. And if we took this contour here, we could say that, okay, IR goes into the contour, so it has to equal everything going out of the contour, which is I3. So IR equals I3. Great. One more. We don't have anything there, right? So we don't have any relationship to write down. Well, actually, we could just say, we know I4 is going to be equal to 0, right? So we could write that. I4 equals 0, because current can't flow out the end of a wire. Of course, if you connect this up, like you would, I've never seen anybody make a microphone and then not connect it to anything. So there's going to be more circuitry to happen, but for the sake of this model, we're not going to model that part. Okay, so there are our continuity equations, our compatibility equations. We have each of these links, right? So passive links. So we say that Vk equals Vm, Vb equals Vm, V1 equals Vm. So Vk equals Vm, Vb equals Vm, and V1 equals Vm. Great. Over here we have V3 equals negative Vr plus V2. So we have V3 equals negative Vr plus V2. And that's all we've got. Question? Okay. So we're pretty much done at this point. I think it would take me more than a couple minutes to type this in, but what we would do by hand is we would do these substitutions straight across and eliminate all our secondary variables. Straight across. And that would be a good start toward getting our state equations. We need to get it down to 2 equations, right? Because it's second order. So there's going to be a lot of substitution happening. This would be one that would be pretty conducive to using software for, because a lot of algebra steps here. So you could use the statement software, for instance, or any computer algebra system really, and we could end up with a state model for it. I think I'll return to this example next semester when we do frequency response analysis, because that's actually what's most interesting to the audio aspect, is what kind of frequency response does it have? How thick should I make something to get a resonance in the right place? How much tension should I put on there? And actually, there's an interesting, the premier maker of this type of microphone actually has like a how it's made kind of video, and it's really cool. I mean, it's like by hand making the foil, mounting it in there, and tensioning it, and then they actually do a test on the tensioning. They don't have a tension measurement. What they do is they actually tension it until the resonance, so it starts to vibrate at the right resonance. So it's pretty cool how they actually construct these.
So like while they're tensioning it, they have the noise already playing?
Mm-hmm. And they want to see, they have essentially an input to it happening, and they want to see, once it's at the right tension, it'll start to vibrate. And so that's, then it's at the right tension. Pretty tricky. I like that. That was fun.
That sounds like a horrible.
Yeah. I mean, it looked like it was kind of cool. It was very like craftsperson-y, like you just like really nicely well-made machinist type
You just
stuff.
need like headphones.
Yeah. Oh yeah. Very tedious. All right. That's all I've got for today. I'll see you guys on Friday.